On this video, I am going to solve the problems for the third symbolic logic, predicate logic homework problem set. And that's what you see on the screen right now. Using this interpretation that now has two place predicate expressions that are highlighted there. LXY meaning x is less than y, GXY meaning x is greater than y, and PXYZ and SXYZ are three-place predicate expressions. PXYZ means the product of x and y equals z. SXYZ means the sum of x and y equals z. And then we're going to let the little letters A, B, C, D stand for the numbers 1, 2, 3, 4 in that order. So when we start out, the first problems are very straightforward. The thing that you're given, 4 is not odd, but 3 is. Notice that it just has the form that you're familiar with, not P and Q. I mean, it just has that shape, right? A negation of a left-hand conjunct and the assertion of the right-hand conjunct. But just means and. And instead of using statement letters, we use the predicate symbols that we're given, as you're starting to become familiar with. O stands for the thing next to it being odd. So we have 4 is not odd. It's not the case that O applies to, and then we put the letter that stands for the number 4, D. But 3 is odd. O does apply to C. 4 is not odd, but 3 is. And it's almost like statement logic, right? Except we've gone a little deeper into the grammar of each statement. So we have a subject and predicate now, not just a whole statement being represented by a letter. 3 is greater than 2, but less than 4. So we have to remember, looking up here, greater than is GXY. The greater thing goes on the left. The other thing goes on the right, and then 2 is represented by B, and 4 is represented by D. So 3 is greater than 2, greater than 3, 2, C, B. So 3 is greater than 2, and 3 is less than 4, less than 3, 4, D, right? That's just a fancy way of saying right, if we wrote it in arithmetic symbols, it would be 2 is greater than, 3 is greater than 2. So we'd write 3 is greater than 2, and 3 is less than 4. 3 is less than 4. We could write it that way, but we're using the letter G to stand for the greater than relationship, and we're letting the letter L stand for the less than relationship. And instead of using the numeral 3 and the numeral 2 and the numeral 4, we're using, to represent those numerals, we're using C, B, and D as if they were numerals in this predicate logic symbolization. Okay, 2 times 2 equals 4. So the product of 2 and 2 equals 4. And in a sense, 2 times 2 equals 4, you know that, so what you want to say is B times B equals D, because B stands for 2, D stands for 4. So if you actually were to go back up here to this representative here, what you want to say, what you intuitively are saying is 2 times 2 equals 4, right? That's what you want to say. And the B stands for 2. Oops. B stands for 2. And D stands for 4. And now just put those over here. There's a B that's in the place of X. There's a B that's in the place of Y. And there's a D that's in the place of 4. And that's the symbolization, actually. This bit right here. So I'm going to copy that. I'm going to return this to how it was. And bring the answer down to line 3. The product of 2 and 2 is 4. 1 plus 2 equals 3, but 1 times 2 equals 2. So if you were to write it in arithmetic, of course, you'd write 1 plus 2 equals 3, but is just and. 1 times 2 equals 2. Well, you know how to say the sum of this and this is this, and the product of this and this is that, right? Use S for the sum. Sum of A stands for 1, and B stands for 2, and C stands for 3. The sum of 1 and 2 is 3, and the product of 1 and 2 is 2. Right? Oh, I'm sorry, that should be A. The product of 1 and 2 is 2, equals 2. Moving to the next statement. Now here, there is at least one number such that there is at least one number that is greater than 2. There is at least one is going to be, there exists an x, so let's put, now we have our first quantifier for this set of exercises. Oops, I lost my my bar there. Let's see here. Where do I go to get that? Well, let me get my symbol from over here. Let me finish this exercise, and then I will pause this and pick it up after I restore my my screen. So there's at least one number that is greater than 2. There is at least one x. And when you say there is at least one x, there is at least one, and you're always talking about something in the domain. So the domain is numbers, right? Natural numbers, 1, 2, 3, up to infinity. Okay? So when you say there is an x, you're saying there is at least one, and you're always talking about whatever is in the domain. So there's at least one number such that it is greater than 2. There is at least one x, and what about x? Well, intuitively, you're saying x greater than 2, right? There's at least one x such that x greater than 2. But the way we write it is using the g for greater than. X is for, there exists an x such that x is greater than, then you put the letter that stands for 2, b. There exists an x such that x greater than 2. I'm going to pause for a second and restore my screen. I'll be right back. Okay, we're back. I found the button to press right up here on my screen. I wasn't sure which one to press, but this makes, you can get a pull down and you can hide or show, and somehow I must have hit a shortcut that closed it. I don't need this here though, and I'm not sure how to make, that collapses it. Then I can restore it. But somehow I got this tab down here now. Well, we'll just go on with this, figure that out later. So every odd prime number is greater than 2. So every odd prime number, when it says every, you're talking about the universal quantifier. So you're saying for every x, if x is odd and prime, then x is greater than 2, right? So let's do that in another step. So for every x, if OX and PX, so if x is odd and prime, then GX and B stands for 2. For all x, if x is odd and prime, then x is greater than 2. And this is a form of It's just a form of all A or B. It's really just a form of all A or B. What you're saying is all O and P are G. I mean, I've abbreviated a little bit. So if you were to plug in some variables, all OX and PX are GXB, right? All things that satisfy being odd and prime are things that are greater than 2. So it's the all A or B form, ultimately. For all x, if AX, then BX. For all x, if this, then that. And the way we represent that, finally, is with the universal quantifier. For every x, that's just our universally quantified expression for all x. And then I'll put a bracket in because I'm going to use parentheses right away to distinguish the antecedent. If OX and PX, the then is just the arrow, then GXB. For all x, if x is an odd prime, then it is greater than 2. So I'll put that for my answer here. And number 7. Let me see, how many more do I have here? I'm not sure. Oh, quite a few. Okay. There is no even prime number greater than 2. There is no even prime number greater than 2. A couple ways you can do it. So there is no, so let's see how to look at that. There is no equals there does not exist, right? There is no, so if we said there is no x such that, what we're saying is there does not exist an x such that, right? So there does not exist is the negation of the existential. There does not exist. So going back to there does exist, sometimes it's easier to say it in the positive and then just negate it. So this says there is an x such that, and to say it's not the case that there exists an x such that, you just put the negation in front of it. There does not exist an x. It's not the case that there is an x such that. What about it? It is an even prime and greater than 2. So x is even and x is prime and greater than x2. B stands for 2. There does not exist an even prime which is also greater than 2. And again, I just use the brackets so that I don't have parenthesis, parenthesis, then you get confused about, you know, what's the left-hand parenthesis. In this one, you probably wouldn't get very confused, even if I used, you know, just parentheses there, because it's a relatively short expression. But if things get longer and have more parentheses, it's convenient to use the brackets so you see what left-hand part goes with what right-hand part. Another way to say this, that's also very intuitive, there is no even prime number greater than 2, is to think of it as saying for all x, if x is an even prime number, then what? There is no even prime number greater than 2. If x is even in prime, then it's not greater than x2, right? And actually, there is a propositional logic thing that's going on here. We are actually, if you think of this negation that I'm highlighting here on the left and the negation here when it is on the right, what you're actually using, without taking, you got to take account of the quantifier. I haven't said how you work with a quantifier there. But what you're actually doing is, in propositional logic, you're doing something like this. You're going not P and Q, and you're turning it into if P, then not Q, right? Because by De Morgan's law, this here equals not P or not Q, and then by implication you get if not P, if P then not Q. So if you kind of ignore for the moment these quantifiers and just look at the internal part, when you take this negation and drag it through, you're going from the negated conjunction to this conditional here, just like in these propositional expressions. Okay, let's go on to 8. I'm going to save this here now as solutions. I'm going to save what we're doing here. And then I'll post this. So, continuing on. Number 8. If one number is greater than another, then their sum is greater than each of them. Okay. If one number is greater than another, then their sum is greater than each of them. So what we're saying is, for any x and any y, and now we've got two quantifiers here. This is the first time we've had two quantifiers in a statement. For any x and any y, if gxy or gyx, then there is a z such that greater than zx and greater than zy. That's a pretty darn complicated one for this level. So if one number is greater than another, so for any x and y, if x is greater than y, or if y is greater than x, then their sum is greater than each of them. And the way we have to say their sum is greater than each of them, we have to say there is something, whoopsie, such that, and I forgot something here, that the sum of x, y is z, and there is a z such that z is the sum of x and y, and z is greater than x, and z is greater than y. So let me expand on it just using arithmetic symbols. We're saying for any x, oops, for any x and any y, if x is greater than y or y is greater than x, then there is a sum x plus y equals z such that z is greater than x and z is greater than y. If you wrote it in arithmetic symbols, it would look more like that. For any x and y, if x is greater than y or y is greater than x, then there is a sum x plus y equals z such that z is greater than x and z is greater than y. So you have to recognize that this is what's being said, and here we have to use the tools to say of the symbolization to say there is a sum, which is using the S symbol. So for any x and any y, how do we say this part? For any x and any y, how do we do that? Well, for any x, and then we add another quantifier. And for any y, there's no word and there. For all x, for all y, we just put one quantifier after another. You do not do this. This is not allowed, right? So this here, this is a no-no. You want to always have multiple quantifiers if you're quantifying over more than one variable. For all x and for all y, if x is greater than y or y is greater than x, put in the proper OR symbol there instead of the letter V. Then, we know how to say then there is a Z. We know how to say there is a Z with the existential quantifier. There is a Z such that, and we just get the parentheses, Z is the sum of X and Y, and it's greater than y, X, and it's greater than Y. And here's an example where having the brackets does help us distinguish what's going on. Notice that I had to put parentheses right here. I just had to put them somewhere, right? It doesn't really matter because you have an AND together with another AND. So if you have, you know, P and Q and R, anything of that shape, you're going to either have to have parentheses on the right-hand side, or you could have put parentheses on the left-hand side like this. Because whenever you have an expression in, if it's using statement logic connectives, there's always a left-hand side and a right-hand side. There always has to be a left-hand side and a right-hand side when you use a two-place connective of any kind. So you've got to put those parentheses in. So that's a kind of hard one, maybe for this level, because you got so much going on with the quantifiers. It kind of jumped to a more complicated level here with all of these. Okay, there's at least one number, for number 9, there's at least one number that is greater than 1 and less than 3. So there is at least one X such that X greater than 1 and X less than 3. So there is at least one X such that, existential quantifier. What about that X? X is greater than 1, greater than X, and then we put in the symbol for 1, and X is less than 3. So less than X, and we put in the number for 3. At least one number is greater than 1 and less than 3. Number 8 is kind of out of place in the order of complexity. That kind of should be at the end. I don't know why I put it there. Every prime number greater than 2 is odd. So, for all X, so it is, as soon as I see every prime number greater than 2 is odd, I'm thinking to myself, this shape, all A are B, right? I'm thinking to myself, whenever I see anything with the form all A are B, I'm going to think to myself, for all X, if AX, then BX, where the A and the B, you know, are some kind of formulas, right? They say, if blah-de-blah-de-blah about X, then so and such about X. If one thing is true about X, then another is true about X. In this case, what we're saying is, for all X, if X is a prime number greater than 2, if X is a prime number greater than 2, then X is odd. So for all X, we know how to say that. For all X, if X is a prime number greater than 2, we know how to say it is a number because that's just what's in the domain. We don't have to add a predicate for it. For all X, if X is prime and it's greater than 2 and greater than X B, so we've got to put some extra brackets and parentheses in here. Then X is odd. So then is the arrow. being odd applies to x. All prime numbers greater than 2 are odd. Number 11, if any two numbers are even, then their sum is even. So we have two numbers now, two quantifiers. So we're going to have for all x and for all y. So if any two numbers are even, then their sum is even. So if even x and even y, so if x and y are even, then their sum is even. So then there exists a z such that z is their sum and z is even. You have to say their sum is even. And the way you refer to their sum is you're referring to the z, pardon me, the z that equals x plus y. So you got to say then there exists a z such that sum x, y, z. So for all x and for all y, if x and y are even, then there is a z, where z is the sum of x and y, and we're going to say that sum, z, is also even. Then their sum is even. For all x and for all y, if x and y are even, then there is a z, that's their sum, and what about that sum? It's also even. If any two numbers are even, then their sum is even. Okay, no number is greater than or less than itself. So we saw earlier how to say there does not exist. No number means there does not exist a number. So it's not the case that there exists an x. What about it? X greater than x or x less than x. So there's not an x such that greater than xx or less than xx. There is no number such that it is less than itself or greater than itself. And another way to say this is, if you bring that negation through, if you can think of, again, I'll talk more about this quantifier. We're going to pull the negation through. But if you ignore that and you just think of the not p or q part, that's going to equal not p and not q. If you think of if you ignore the quantifier, if you bring that negation in, we're going to get a universal quantifier here. And again, I will talk about that. For all x, not gxx and not lxx, right? For all, if there does not exist an x such that x is either less than or greater than or less than itself, that's the same as saying for any number you pick, it's both not greater than itself and it's not less than itself, which is how you would do that. Okay, I'm going to post this, and I hope that it has been useful to you.